Assalamu alaikum. We have learned about galvanometers, which are used to measure the current in a circuit. In this video, we'll discuss about moving coil galvanometers in detail. Now, before going ahead, let me tell you what these moving coil galvanometers do. Moving coil galvanometers are used to detect the presence of current in a circuit. It means they are used to measure the current in a given circuit. How do they work in such case? These moving coil galvanometers work on the principle of torque experienced by a current carrying loop in magnetic field. We know when a current carrying coil is placed in uniform magnetic field, it experiences a torque. That is the principle behind the working of moving coil galvanometer. The principle is nothing but torque experienced by a current carrying loop in a uniform magnetic field. Uniform magnetic field. Clear? Okay. Now I go ahead. I will show you how the moving coil galvanometer appear. It consists of a rectangular coil. Consists of rectangular coil. I name this coil as P Q R S. It consisting of large number of turns of thin enameled copper wire wound on a light metal frame which is rectangular in shape. Okay. This coil PQRS is suspended with the help of a phosphor bronze strip which is connected to a torsion head represented by letter T. This is the torsion head which is represented by letter T, to which the phosphor bronze strip is connected, and with the help of this phosphor bronze strip the rectangular coil is suspended. Okay, and apart from this, this phosphor bronze strip is provided with a plane mirror, a small piece of plane mirror which is used for the measurement of current with the help of lamp and scale arrangement. Clear? Then the bottom, that is a QR of this rectangular loop, is connected to a hair spring, a fine hair spring consisting of few turns. It is also made of phosphor bronze strip. This one is connected to this end of the spring is bound to a binding screw. This is connected to a binding screw at the bottom. Okay, this is the setup. This is how the coil of the galvanometer is arranged. Okay, then this entire setup, this rectangular coil is placed between the pole pieces of horseshoe magnet. Now, which appears something like this. This is the north pole of the horseshoe magnet, and this is the south pole of the horseshoe magnet. Now, if you look at them carefully, you will find that the inner side of the magnet is a semi-spherical in shape. Okay, it is used to provide a radial magnetic field. Now, what is that radial magnetic field? I will show that to you later. Now, this is the structure. This is the construction of moving coil galvanometer. The entire setup is placed inside a wooden frame provided with glass, okay, such that it should not get disturbed by air in the surrounding. Then this end, this end of the phosphor bronze strip and the hair spring, both are connected to the external terminal through which we pass current for the measurement. Right? Now, I was telling you about the radial magnetic field. Now, let me show this to you. This radial magnetic field appears something like this. Where shall I show this to you? Okay, I draw this one here. This is the north pole. This is the south pole of the horseshoe magnet, permanent magnet, and between them the coil is placed. Now, if you look at the coil from the top, it appears something like this. Now, I was telling you about the radial magnetic field. Now, radial magnetic field appears something like this. So, what is the purpose of radial magnetic field? This radial magnetic field makes the coil to remain parallel always with the magnetic field. Okay, see, this magnetic field makes the coil to remain in a parallel condition. You can see, suppose this is the state, this is the position of the coil, then it is parallel to the magnetic field. Suppose it has suspended, it has moved to this position, then again it will remain parallel. If it has moved to this position, again it will remain parallel to the magnetic field. So we call this kind of magnetic field produced by the semi-spherical pole pieces as radial magnetic field. Radial magnetic field. Magnetic field. It plays a very important role in the functioning of this moving coil galvanometer. Fine. Now we will go ahead. Now I am going to get the expression for current measured by this moving coil galvanometer. Now, before going ahead, let me take this part of the galvanometer. This is nothing but the coil. Okay, coil P Q R S. Now, as the north pole is present here and south pole is present on the right side, so the dotted lines represents the magnetic field acting in this direction. So this clearly shows that magnetic field is acting perpendicular to P and Q in this direction. Okay, this is the direction of magnetic field, representing letter B. The same here as well. And how the current flows in this coil? Current is shown by this arrow mark, direction of flow of current. Suppose here I have taken a rectangular coil with the number of turns equal to 1 and through which a current I is flowing. Now, for my convenience, I do so. Then the current I flows in this way through the loop. Okay. Then if it is so, I told you earlier, it experiences a force. Here, the ends PS and QR. These two ends are always remain parallel to the magnetic field according to this diagram. They remain parallel to the magnetic field. As a result, they experience no force. So here, ends PS and here this is the breadth PS and QR provides the breadth of the rectangular coil. Okay, so these two remain parallel to the magnetic field, so they experience no force. Remember this. The next thing from the diagram here, PQ and RS. PQ equals to RS. These two provides a length to the coil. So, the length of the coil is L. Breadth of the coil is B. As shown here. P, Q and RS. These two remain, they always remain perpendicular to the magnetic field. So they experience a force. In what direction these forces will act? Let me show this to you. To get the direction of force acting on PQ and RS of this current carrying loop is given by Fleming's left hand rule. Now let me show this to you. If you stretch 3 fingers of the left hand, then they provide a magnetic field, the direction of flow of current and the force acting on those current carrying loop or conductor. In that way, this is the direction of flow of current given by the middle finger. It acts downward this way, and index finger represents the magnetic field which acts towards right side. If it is so, then the magnetic field will act, the force experienced will act as normal to the plane of board in the outward direction. So I can say here, this is the force, direction of force which acts outward. It acts outward. Then what about the direction of force on the side RS of the current carrying loop? Now according to the diagram, the current flows upward. This is the magnetic field. Then the thumb represents the direction of force. It acts inward. So this is the direction of force. It acts inward. What does it act? It acts inward. I hope I have understood. So there are two forces acting on this current carrying loop. One in the inward direction, another in the outward direction. So these two forces constitute a couple. Well, let me take it this way. This is our coil, the plane of the coil. Good, so one force acts upward, another force acts, there is one force acts inward, another force acts in the downward direction. These two forces are acting in the same plane but opposite to each other. So they constitute a couple. These two forces constitute a couple. What is this couple? Couple is nothing but a pair of forces acting on an object in the same plane but opposite to each other. Okay, two equal and opposite forces acting on an object is usually referred as couple of forces. This couple of forces makes or provides a torque to this current carrying loop. Now which is suspended with the help of phosphor bronze strip. This is a phosphor bronze strip. Remember this. Okay. Why phosphor bronze strip is used here? That I will tell you at the end. Let's go ahead. Now when we pass current, it experiences torque. As a result, it rotates. When it rotates, this phosphor bronze strip experiences a twist. First, the torque experienced. It is written this way. Oh, I call it as deflecting couple. It deflects, isn't it? Deflecting couple. There is nothing but torque. Nothing but torque, represented tau, is equal to the product of perpendicular distance. We know torque is calculated by multiplying perpendicular distance. What is that perpendicular distance? Here from the diagram, the perpendicular distance from this force and between these two forces is nothing but this. Is represented B. Okay, that is the breadth of this rectangular coil. So perpendicular distance multiplied with any one of the forces. We take any one of the forces. Yeah. Here the perpendicular distance is B and the force is F. And we know, so I take it as tau. F, the force acting on a current carrying loop, is given as BIL. This we have learned earlier, BIL. So this can be rearranged and written this way as BILB. When we multiply length with breadth, we get area. So from this diagram, from this tau is taken as BIA. Here when L is multiplied with B, we get the area. That is the A. Okay. This is a torque experienced, the deflecting couple experienced by a coil consisting of only one turn, single turn. If it consisting of n number of turns, then the torque experienced will be given as tau equals to NBIA. This is the torque experienced by a coil, current carrying coil consisting of n number of turns. Remember this. I take it as equation number 1 for my convenience. Now, I told you earlier, due to deflecting couple, a restoring couple, now this phosphor bronze strip gets twisted. Once the flow of current stops here, it returns back to its original position. So, as a result of this twist, a restoring couple is built here, which makes it to come back to its original position once we stop the flow of current through it, through the coil. Clear? So I just measure that. I calculate that restoring couple. Restoring couple. This restoring couple is also represented by letter tau. Is found to be directly proportional to. This restoring couple is found to be directly proportional to angle of twist. To what angle it gets twisted? That is the theta. Fine. And we know if you have proportionality, now here I write this, tau is directly proportional to theta. Now when I remove proportionality, I have to include a constant here. So this way, it can written as tau equals to constant multiplied with the theta. Theta is angle of twist or angular twist. Remember that. So I provide this constant with a letter. This time tau is written as tau is equal to the place of constant. I write k. K is the constant taken here. What is this? Here k is the couple per unit twist or restoring couple per unit twist. I repeat, k is nothing but restoring couple per unit twist. Clear? That is k. Then in equilibrium, at equilibrium, it is found that the deflecting couple is equal to restoring couple. So right at the equilibrium, deflecting couple is found to be equal to the restoring couple. Which is given with this equation. Okay. Now I substitute the values. Here deflecting couple is nothing but given by equation number 1, that is the NBIA equals to the restoring couple given by equation number 2 is k theta. Now from this, I is found to be obtained by cross multiplication. I keep I on the left hand side. The remaining terms are taken to the right hand side of this equation. So k theta is kept as such divided by NB E. Clear? This is the expression that provides us the value of I measured by the galvanometer or the current flowing through the galvanometer. Now, if you look at this equation which I have obtained here, K is a constant. It is nothing but restoring couple per unit twist. And N is the number of turns in the given loop carrying current. It is also a constant. B is the magnetic field. This magnetic field is uniform magnetic field, so it is a constant. And A is the area of this rectangular loop through which current is flowing. So here K, N, B and A are constant here. So this whole is a constant term. So this equation can be written as this way. I write this way. I equals to constant multiplied with theta. Okay. This constant is I represent this constant by letter G. This is the final expression. And here G is the galvanometer constant. Remember this. What is G? G is nothing but galvanometer constant. The value of this galvanometer constant is nothing but this. Now, if you compare these two equations, you will get that from here G equals to K upon N B A. Now, this is the expression of G. It is actually obtained from here, from this. Semicolon here. This is how one can get the value of G and the relation between angular twist and current flowing through the galvanometer. Here, this moving coil galvanometer. Usually, this kind of moving coil galvanometer is referred as a suspended moving coil galvanometer. They are highly sensitive devices. These devices are highly sensitive, so they are always kept fixed at the corner of the lab. While measurement, usually once it is fixed, it is not moved from one place to another place. Now this may disturb the setup of this galvanometer because it consisting of a thin strip of phosphor bronze wire. So if you move this, now and then it will get damaged. And a second thing here, the phosphor bronze strip is used for the reason that it have the least value for K. K of phosphor bronze strip is very low. So for that reason, it is chosen. It is a kind of alloy. Okay. Now let me tell you what is the sensitivity of a galvanometer. Suppose a given galvanometer is capable of detecting current, least current flowing through this. Suppose you pass a very small current through the galvanometer, and even for such a low current, if it shows the deflection, then we call such galvanometer as a sensitive galvanometer. And suspended moving coil galvanometers are capable of measuring current equal to 10 power minus 8 ampere. This much of current can be measured with the help of this kind of suspended moving coil galvanometer. And a second thing, usually I might have shown this kind of galvanometer to you. Here, this rectangular loop is provided with a pointer which runs on the scale to show the intensity of current flowing through the circuit, and it is also used to check the direction of current. This kind of galvanometers are called as pointer type moving coil galvanometer. They are less sensitive, so they can be used in Wheatstone bridge or along with the meter bridge or potentiometer for the measurement of current or to detect the direction of current. But I suspect the moving coil galvanometers are highly sensitive. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your question in the comment section. Thanks for watching.